Welcome to the Building Science Podcast.
Bringing the human factor to construction, design, and architecture. Brought to you by Positive Energy in Austin, Texas.
Hey everyone, and welcome back to the Building Science Podcast. I'm your producer, Michael.
Hello, I'm Christoph Irwin.
And we're here to dive into episode 5 of our 5-part series on the control layers. And this week's episode is going to dive into the thermal control layer. As you can imagine, we probably have a lot to say. So get your notepads out, put your kids to bed. It's time to dig in.
Yeah, hopefully I'll be able to get through this in a coherent manner, because I do see a lot of topics that are interlocked and interwoven. And here we go. So we're talking thermal control layer. And the first thing we need to understand is that we are talking about R value. That's what I think comes up for most people when they think about thermal control. They think insulation and they think R value. That's good. You're in the right category. But what's happened that's not great is that people are equating thermal control with quality. So there's something out there like a gestalt that says, well, I want to build a good building. I want to be able to be recognized as a good builder. Therefore, I need to have high R values in my building assemblies. And then the higher the R value, the better. That's totally not true. What you want to realize is that the thermal control layer, in terms of priorities, is not the number one priority, right? We've talked about this already. First thing you're doing is you're saying, I want a high quality building. It means I want a high quality environmental separator. That means I want to make sure my building doesn't leak the outside to the inside. And what can't it leak? It can't leak water, liquid water. It can't leak air, and it can't leak water vapor. So most of the water vapor is going to come through the air, be carried with the air. You don't want it to leak vapor in certain circumstances. And now we're saying you also don't want it to leak heat. So you want to keep the outside out and the inside in. Let's say it's winter. You want to keep the warm air inside your house in. You don't want it to leak out. You don't want the cold air that's outside to leak in. And the flip side, here in Austin in the summer, you want to keep the heat outside and the cool, dry air inside. Couple of things, and we've talked about this in the intro. We want to make sure we understand that in terms of which way is downhill, think about it now, which way is downhill? Is it hot to cold or wet to dry? Right, it's hot to cold. Uphill is hot, downhill is cold. And what we're really measuring with that uphill is molecular vibration in the air, and it's going to move toward areas that aren't vibrating as much. Digging in more to the conventional or mainstream end of thermal control layers, we're talking about heat transfer, and we're talking about slowing it down. Unlike the other control layers, we aren't even presuming to stop the heat from getting in. So let's take an enclosure that we would think would be pretty awesome, like the space shuttle. Right, so obviously if it goes into outer space and we put living beings on the inside, it's a really good control layer. If we park that thing in the desert in Arizona and we put a thermometer on the inside, in the summer, let's say, put a thermometer on the inside, are we going to measure the temperature going up over time? Absolutely, right? Thermal energy moves through materials. It moves through materials in 3 ways. And this is when I say big sprawling heap of interconnected thoughts, right? It moves through materials in 3 ways simultaneously in 3 dimensions. And this is where our puny little brains need some simplification. And we take a lot of liberal simplification when we talk about thermal control. I'll talk about that in a minute. But just going through the hierarchy of heat transfer, right? They're typically listed in this order: conduction, convection, and radiation. In a home, it's probably more realistically to say radiation, and depending on the home, radiation, convection, and then conduction. And what do I mean by that, right? So radiation is your windows, your glazed surfaces. High energy radiation from the sun goes right through glass. And when it moves through the glass, it sheds some of its energy to heat the actual silicon in the glass there, silicon oxide, and keeps going, gets to the inside of the building. But now, since it's lost some energy, it's downshifted. It's no longer shortwave infrared, it's long wave infrared. And the funny thing is now which is now that it's long wave infrared, glass is opaque to long wave infrared, so it doesn't go right back out. Right? This is the greenhouse effect. Once the heat gets in, it doesn't go right back out. And what we do, we have fantastic materials. Right? We have, in terms of window materials, we have fantastic materials generally, but in terms of glazing, we put these metal films. We sputter on very thin layers of various metals in various configurations to limit, and very effectively limit, the amount of shortwave infrared that will come through a piece of glass. It is still a big deal, right? That's in terms of the rest of the wall assembly or the roof or the foundation. If you're thinking about heat flow broadly, in terms of thinking about thermal control broadly, the aperture that is the window, that is the hole, or as a good friend of mine, Matthew Tanteri, has referred to as the thermal wound of the building, we need to bring the window and the doors, the massive sliding glass doors, into the conversation and realize that a building is there to deliver comfort for the occupants, and that when we want to do that, we want to have good thermal control, and that means that we got to talk about windows and doors. Yeah, so I've kind of gotten pretty far down the ladder here on radiation, and if you want to learn more about radiation and radiant energy, we did a podcast earlier on thermally active surfaces and radiant heating and cooling. There's more about that. Radiation through your windows is a big deal when it comes to thermal control, and what I find striking is that it's often left out of the conversation. People want to jump right in and start talking about insulation, which we're going to do. But first we're talking about the sort of the hierarchy of how heat moves from outside to in, and we've covered radiation. The next one is convection, or air leakage. Air in Austin in the summer carries a lot of energy. Air in Boston in the winter, the indoor air has a lot of energy in it that you don't want to get out. So if air is able to move through from inside to outside, then that has affected the ability for the enclosure to control the thermal environment. The thermal control layer has a massive leak. And I'm fairly confident that a lot of us listening to this, a lot of you guys listening to this, are familiar with blower door metrics and air changes per hour and the building codes. So an air change per hour at 50 pascals, code standard here would be 5 air changes per hour at 50 pascals. Slightly north of here it goes to 3, and that's no slouch. Those are good numbers. As we know, there are much lower thresholds that are possible. Organizations like FIAS are requiring 0.6, and they're even doing better than that. They're requiring 0.05 per square foot of enclosure. The whole idea of normalizing leakage by the floor area when the leakage surface is not the floor area is a little suspect, but it's also part of the industry. Circling back into what we're talking about convection, and I just want to point out that if you have air leaking from inside to outside or outside to in, and air is carrying thermal energy with it, then that's important to think about when you're thinking about your thermal control layer. And again, people think about insulation when they think about thermal control. They don't think about their windows, and they don't think about their air control layer, which are actually, the reason they're higher on the priority list is because they're higher on the damage to the functioning of your thermal control layer list. The last one, which is the most talked about one, is conduction. And conduction is heat moving through the materials, right? So let's say you painted your building a dark color. There's a lot of dark brick that's very popular now, and downtown Austin even has some buildings that are in, a very lovely dark gray or a dark black. Dark red. Dark red. And that color absorbs a lot of heat. It's going to soak it into the material, and then where is it going to go? Well, if you could instantly make it night, well, it's going to radiate back to the outside. But if it's still coming in from the outside, that heat is going to start to move through the material. And if it's brick, it's going to hold a lot of heat, and it's going to start driving it through the material. It's going to then encounter the air gap. It's going to shoot across that by radiation very effectively. And then it's going to encounter the control layer. It's going to go right through that by conduction. It's going to go, that is touching the sheathing. It's going to go through that. And then it's going to counter the insulation. So keep in mind, conduction only works if you're touching something. If you look, there's a famous picture. Can't show it to you on a podcast, but imagine the bottom of an iron, like the iron you would iron your clothes with. And let's say I painted one side of the iron bottoms are typically shiny silver. Let's say I painted one side of it black. And then I look at that with an infrared camera that measures radiation. So what I'm going to see is, I'm going to see a picture that is extremely misleading. I'm going to look at the black side and I'm going to say, whoo-wee, that's hot. It's probably going to show up as white in terms of heat. It's going to show up as a very strong amount of heat radiating off of the bottom of that iron. And I'm going to look at the silver side and it's going to look a lot cooler. So I'm going to say, well, check it out. I painted the bottom of my iron half black and only the black side gets hot. As far as radiation is concerned, that's correct. If you lick your finger and you touch the cool, shiny silver side of the iron, you're going to burn yourself. Why? Because that's conduction. You're not thinking about radiation. So silly things that happen in the building industry category, people put radiant barrier roof decking on their roof, which means that decking gets very, very hot, but it doesn't radiate a significant portion of that heat to the inside space. Instead, it holds it and eventually, hopefully, will radiate it back to the outside. But then they say, okay, I got that radiant barrier. That's pretty cool. Now I'm going to put spray foam insulation up against it. Well, as soon as you touch it, it is no longer a radiant barrier. It's in conduction mode and it's going to move right through, which is where we were when I was talking about the dark colored brick or painted siding of any sort conducting energy through the building material. At some point, it could be outside the control layers, it could be inside the sheathing, it's going to encounter the wondrous insulation material. And there's a broad class of products and materials that we'll talk about now that try to interrupt the flow of thermal energy through that material. And it's important to realize here that the insulation leaks, right? It's a thermal retarder. It slows down the length of time that it takes for heat to get to the inside space. Now, there is another pretty awesome material that I like a lot. I think it has good promise for our industry, and it's a phase change material. And when installed right and put in the right way, and there's so much to say about phase change material. Its abbreviation is PCM. So when thinking about putting PCM in the walls, you do encounter for at least a period of time until it is saturated, you encounter a material that absorbs the thermal energy, that holds the thermal energy. It's not just slowing its flow, it's actually preventing its flow at that point. And then eventually it melts, it does the phase transition from solid to liquid, and now the wall is no worse off than it would have been before the PCM. So PCM is so prominent in our thinking right now that in fact it was our first podcast. It was on our mind at that time and we started doing these recordings. So I encourage you to go back and listen to that, and we will definitely dig into that deeper in the future. Back to where we were. We were talking about insulation and insulation materials, and we were talking about them, we arrived at talking about them by realizing that in terms of a thermal control layer on our building, priorities would be first radiation, most likely, and then convection, and then conduction. So what we have is, we have thermal control trying to be accomplished by insulation materials. And even within an insulation materials, those three heat transfer functions are occurring. And those are what we use cleverly to prevent or to retard thermal energy movement through a wall, to keep the heat out and the cold in, or vice versa. So specifically, what we're talking about when we talk about insulation, let's just list a few. Think about some insulations, right? You guys are listening and probably all know about some insulation products. So most of the original ones were fluffy, right? Early on, people used sawdust, cotton, various organic fluffy things in their wall assemblies and in their building assemblies because they did what? They trapped air. Air is what actually is used as the functional ingredient in all insulations. It just is a matter of how it is used. After the war, World War II, during the war, I think it was the Germans that had invented or perfected the ability to make fibers, very small fibers, out of glass. And they could make mats of that and use this fibrous mat as a way to trap air and to prevent thermal, or to slow down thermal energy transfer. And here's how that worked. So imagine you could zoom in to a fiberglass bat. What you would see is a few small strands like hair strands of glass moving this way and that. And along those strands, you could have conduction occurring, right? So glass is a very poor conductor. It's a great insulator, implicitly in terms of the material, so the conduction is low. You also have all around those strands moving every which way, you have trapped air. So the only way for heat to move through that is for the air to move through the material, which unfortunately for bad insulation, it can move right through. Any fluffy insulator you have in your building, convection or air transported heat is not thwarted by that material. Before I move on with that thought, you also have, you have these various strands, and they're not all at the same temperature. So any strand that is hotter than an adjacent strand is going to do what? It's going to radiate from that strand to the adjacent strand. So what we have is with fiberglass bats, or I shouldn't just say that, with fiberglass, blown in fiberglass bibs, with mineral wool bats, with cellulose, all of these things, what we have are materials that don't conduct very well. They're limited surface areas, so they don't have much surface to radiate from fiber to fiber, and they trap air, which insulates. When you're using a fluffy material, your main downside is air movement, right? If you have a fiberglass bat, I keep going back to that, or a mineral wool bat, or any blown-in fluffy material, to make it a good thermal control layer, it has to be contiguously in contact with an air barrier. And except for situations where the thermal control layer is horizontal, like at the floor of an attic, if it's on a wall, an attic knee wall or your wall, that air barrier needs to be in contact with all 6 sides of that radiation. Of that insulation. So think about, zoom inside your wall there and think about a stud cavity. It's a long, skinny rectangle. And by the way, it's probably got holes in it because you've got plumbing and electric wires moving through it, so that helps with airflow. And that long, skinny rectangle, it has studs on 2 sides, it has a top and a bottom plate on the top and the bottom, and it has your interior wallboard and your exterior sheathing on 2 sides. So it is surrounded by 6 sides. So now let's say I did open cell spray foam. Well, really, it's quite similar. It's a fluffy material. It's more, I guess, frothy would be more accurate. And it's created by an expanding, like shaving cream that suddenly hardens. Polyurethane spray foam is, in terms of molecularly, it's not any different than a bowling ball. It's like a big, fluffy bowling ball. And you have radiation from cell wall to cell wall, and you have conduction through the cell walls, and you have extremely limited convection because these cell walls, there's holes in them, but they don't align in one consistent direction from inside to outside. This is how it ends up eventually creating an air control layer. Now, if it's closed cell spray foam, you still have conduction through the cell walls. You still have the ability to radiate from one side of the cell to another, from a hotter surface to a colder surface. You can never stop that one. And you do have better limited convection, right? So air does not move right through these closed cell layers. I guess the most important thing to take away here is that what's really happening is that all these things are happening at once. You're having multiple 3-dimensional interlocking conduction, radiation, and convection paths occurring at the same time. Now, we don't usually think about this. And our models, most of our energy models, they're getting better. I'm not going to berate energy models. But most of the time when we think about thermal control, what we think about is the outside of the wall is at the outdoor design condition, which here in Austin in the summer is 100 degrees, and in the winter it's 30. And the inside of the wall is at the indoor design condition, which here in Austin in the summer is 75 degrees, according to ACA, And the inside surface temperature in the winter is going to be 70 degrees. So let's go back to summer. So what we have is we're thinking about thermal transport through our wall, and we're thinking about it as being a uniform surface temperature on the outside and a uniform surface temperature on the inside. Well, right away, you can see that's a big simplification. It depends on the time of day. It depends on the solar exposure, right? A dark colored wall in the sunshine is going to be a lot hotter than the air temperature. It's going to be easily 140, 150 degrees, if not more. And then the inside temperature is also varying depending on what's going on in there, and in internal loads and sources of heat inside the building. The next thing we do is we assume that the insulation is homogeneous, which means like uniformly fluffy from the inside to the outside. That's not true, right? So we know that there's electric wires and pipes moving through it, which can compress the insulation. And even our studs, right? We assume our wood is uniform conductivity. Well, wood is, grows in rings. Trees grow in rings. Growth rings.
If you didn't know, wood comes from trees.
So yeah, you can get conduction that goes better along the ring than it does jumping from ring to ring. So wood is not uniformly, the R value of wood, let's just say, is not uniform. It's variable. It depends on which way you're trying to move through there. But we ignore that, right? And then we also assume that the heat transport is steady state. I don't want to go into these too much. This is going to get too geeky. Let's just say there's a lot of simplifications to a very complex process that's going on when we're talking about thermal transport. So there's no way around it when you're talking thermal control layer or thermal transport with your trades or your clients or your builders. I don't know exactly the various avenues you have of communication out here in the field, but people are going to think insulation. And when they think insulation, they're going to almost certainly immediately think R value. So R value, the letter R hyphen word value, is something that is concocted to help the average homeowner relate without too much intimidation to the subject of heat flow. And there's no way around it, but R value has to be considered a physical, it's like a physics term, and it has units. So let's talk about the units. Let's talk about BTUs. So obviously heat is measured in BTUs. Probably a lot of us know that. And 1 BTU is defined as the amount of water, the amount of heat necessary to raise 1 pound of water 1 degree Fahrenheit. So 1 British thermal unit will raise 1 pound of water 1 degree Fahrenheit. That's liquid water. I think there's a setting, it's like in the mid 60s, like maybe 64 to 65 degrees, something like that is exactly a BTU. But generally speaking, from 32 degrees Fahrenheit to 212 degrees Fahrenheit or 211 degrees Fahrenheit, you add a BTU, the water goes up 1 degree Fahrenheit. And that defines an amount of heat, and it's not a trivial amount of heat. A BTU is a large kitchen match burned completely. So a BTU is a lot of energy, and you want to describe its movement through your material. So what you do is you say, well, I really want to know how much energy moved through my material per square foot, and then I know how much energy is moving through on a normalized area. And then I also want to say, well, how much moved through that square foot in a given period of time, and we've picked an hour. In the SI units, they've picked a second. So, but I'm sticking with imperial units right now. So we have a BTU per square foot per hour. And the last thing I need to know is the driving force, right? So I need to know how many degrees Fahrenheit, how steep was the hill? Remember, heat moves from high to low, more to less. So I need to know, is it a steep hill, like a Black Diamond ski slope, or is it the bunny hill? So those 3 factors, the time, the area, and the driving force, are all necessary to understand the heat transport, right? And I guess one of the things that I find surprising is that how many building science seminars you can listen to or attend, and no one talks about the units, and it's like people think that, we can't handle the truth. You can't handle the truth. So I think we can. So imagine this. We're talking about how much energy, so how many BTUs per hour, per square foot, per degree Fahrenheit. That is not R value. That is U value, or thermal conductivity. So that is not the resistance to heat transport, but that is the number characterizing the susceptibility, or the, there's a word I'm not thinking of, but how much heat will be transferred through the material in that time. So what you need to do is you need to flip that number upside down. So if I'm saying, here's how much conduction occurs through my material per hour, per square foot, per degree Fahrenheit, and I flip it upside down, now I'm saying, here's how much resistance to conduction my material has. So if you could think in units, you would say U value is BTUs per hour, per square foot, per degree Fahrenheit, where R value is this crazy unit of hours, square foot, degree Fahrenheit per BTU. So that's a little bit probably farther than I went, and maybe I answered my own question on why people don't talk about this. But I think it's at least interesting to me, and hopefully interesting to you, and at least hopefully useful to you to understand that what we're talking about is something real happening in real materials. We're talking about heat moving through materials, normalized by reasonable things. We don't have to go to trickery here and kind of strange, these are not the droids you're looking for tactics to help you understand this. So that's R value. R value is this measure of resistance to conducted heat transfer through building materials. Now, we use materials with high R values. We want high R values, low U values, right? So what does that mean? Let's do some math. I think everyone would agree, if we were going to pick the poster child for normal insulation, mainstream insulation, it's an R13 fiberglass bat in a 2x4 wall. So one way to think about that and to make it physical is to flip it upside down and do 1 divided by 13. You'll get something like 0.08. And what you're meaning by 0.08 is not some random number, right? You're saying I'm going to get 0.08, so 8/100ths of a BTU per hour, per square foot, for every degree Fahrenheit of temperature difference across this bat, right? And that is where I really think understanding starts to happen, when we realize that these aren't numbers that aren't tethered to real physical occurrences. There's a reason why a higher R value wall blocks more heat flow than a lower R value wall. So if we just think about R value, it's best to normalize it by dividing it by one other thing, and that is dividing it by the thickness of the material. So if we want to compare on a level playing field, it's very useful to say, well, what's the R value? What's the resistance to heat transfer for a 1-inch thickness of my material? And so for that fiberglass bat, so the R value for a fiberglass bat is something like 3.6, 3.5. I'm not going to argue. You might see 3.8. Moving up, in terms of moving up in R value, we're going to move in next to the oil-based products, our polystyrene foam, our polyurethane foam, our polyisocyanurate foams. And 1 inch of thickness of each one of those, right? So EPS, the expanded polystyrene, is going to be around R5 for 1 inch of that. And the XPS, extruded, is going to be around slightly higher, maybe R6. That's where the open cell spray foam is. It's around R6, and that's foamed on site. And there's a lot to say about that. Ooh boy, that's a big topic. I'm gonna not go there. Though then we have polyisocyanurate, which has a different inert gas trapped in it than air, and we get into the issue of its long-term thermal resistance, and that's the number that's quoted, and that's usually quoted around R7, which is pretty much the highest you can get through fairly normal means. R10, or better than R10, can be achieved with some pretty awesome products that are used in things like the space shuttle and the space station. And I'm thinking specifically of aerogel. And you can buy aerogel insulation mats and use them in your buildings. And I think that's a really good idea as we start to get to really getting down to very good quality enclosures and control layers, to think about using aerogel or other insulation with high R value in strategic areas. Okay, a couple more items of interest while we're talking about kind of the numeric or quantitative side of insulation, right? So keep in mind, I'm sure I've said it enough, if not too much on this podcast, that it's not all about R value, but R values are useful to talk about. So let's talk about some other R values, and let's talk about a couple that you might not think about. One is that there's a layer of air, a molecular layer of air, or several molecular layers of air next to your wall, like inside your wall, right there. So if you're in a room right now, or if you're in a car, look at any surface around you and realize that if the air is moving around inside that space, it's able to transport energy. But as you look at the air closer and closer and closer to the surface, the air right at the surface is stationary. It's not moving. So what does that mean? Trapped air at the surface is insulating. And the R value is, it depends on an outside condition. It depends on, inside and outside. It depends both on how fast the air is moving and if the surface is vertical or horizontal. So in terms of vertical surfaces like walls outside, the R value is around 0.1 to 0.2. And it really depends on airspeed, right? It's going to go lower with higher wind speeds. Inside, it's around 0.6 to 0.7. I think it's like 0.6 on the ceiling and 0.7 on the walls. So that's pretty cool. Between the two of those, if we say it's 0.2 outside and 0.7 inside, you're pretty close to an R1 of trapped air R value, just because you have some material there and it's in our atmosphere and there's air trapped. In fact, any airspace, right? So if you do a ventilated rain screen and you have a 3/4 inch furring strip and you're effectively trapping an inch of air, or let's say 3/4 of an inch of air, you're getting another R1 right there. Typically a trapped airspace, just air, is given an R1 between 1/2 inch and 4 inches of thickness. So these old 1920s buildings where people say there's absolutely no insulation in that wall, well, it's kind of funny because the trapped 2x4 stud is, empty stud bay, no insulation in it. Well, that's an R1. And then you get another R1 just from the air films on the outside and inside. And then the materials themselves, right? You're going to have 3/4 of an inch of wood or plywood. That's going to be around an R1, maybe less, R of a half, 0.5 to R1. 1/2 inch sheetrock gypsum wallboard is around 0.4, 0.45, I think. Obviously, slightly thicker. 5/8 is a little bigger. I think it's like 0.55, something like that. So you can see every material you use starts to add R value, and these all add up. In series you add the R's, and in parallel you add the U's. That's beyond this podcast. You can look up how to calculate that stuff. Okay, so we're going to wrap up now by kind of introducing what I said up front, that the windows, your glazed surfaces, they represent relatively large holes in your thermal control layer. And what I mean by that is if you had an R3 wall, you'd be pretty disappointed in that, right? We've been talking about R value per inch for fiberglass, it's above 3. And for aerogel, it's above 10. But we use more than an inch, right? So typical R value in terms of just the insulation value, it's going to be R20, R15 to R20, R30, something like that, 38 at the roof. So those numbers, 15, 20, 38, compare to an R1 for a single pane of glass or an R3 for good glass. You can go with some really awesome glass these days. I mean, there's coatings on layer 4. There's a lot to say about glazings, and you can get an R3 window pretty common these days. But still, relative to the walls, it's a big deal. Another quick tangent on this is the insulation of our ducts, our air conditioning ducts, which when they're in a hot attic, they separate the inside from the outside. That's like an R6. And there's like a little known secret that R6 is separating indoor space from outdoor space, and the amount of surface area in all your ducts in an attic can actually rival the entire floor area of the attic. So here we go sometimes to great pains to make sure that we have a good R38 of insulation, fluffy insulation in our attic. We have all those depth gauges and all that. And you look all around them and you have R6 ducts in your attic. So that's kind of silly, and it's going away, and that's why building codes, rightfully so, are moving away from the horribly misinformed, and I don't know how it got started, practice.
Hey, puppy.
Hey, Lilo. Of putting air distribution systems in hot attics, in cooling-dominated climates. So I guess one more thing's popping into my head before I do the wrap-up. Spray foam, right? There's no way around it right now. Open cell spray foam, closed cell spray foam. Look, she's doing the wiggle dance on the floor.
You'll have to pardon the dogs. They're a part of our operation here.
Yeah, she's up on her back. Now she's coming over for a hug. She's petting. Okay, so open cell spray foam is probably one of the most prominent products that are going to be considered. If you're not using it, you're going to say, I want to step up my game. I'm going to start doing spray foam in my enclosures. And when you do that, generally speaking, open cell spray foam has the property of an awesome wow factor, especially the first time you put it in your building. You walk through the building and you go, wow, look at this. It looks awesome. The acoustic resonance changes right away. The air control layer is improved by the spray foam. But don't be misled by the wow factor. Open cell and closed cell spray foam are fraught with the same installation persnicketyness, that's a technical term, meaning you got to be careful, as other insulations. So what it's got going for it is it looks awesome, and people don't usually question that it is awesome, but it's not necessarily uniformly applied. There can be holes and gaps and cracks. It has to be applied at the right temperature by a qualified installer. There are concerns about indoor air quality. It should go completely inert if it fully cooks off the A and the B side. I can't do it. I can't summarize all the issues that are coming to mind about open cell and spray foam, open and closed cell spray foam here at the end of this podcast.
Perhaps we'll do another episode.
Yeah. We should do one just on open and closed cell. Maybe we'll get our good friend Allison Bales in on that one. He knows a lot about that. So to summarize this whole topic of thermal control, and maybe even tie it into the overall topic of control layers, here's a few things to keep in mind. One is you can't consider any of this stuff in isolation. It's a system of interconnected systems that we typically idealize and create simplifications that lead to inaccurate understanding or inaccurate modeling. So one of the main areas there is that thermal and moisture control are intimately tied. If you have to prioritize one over the other, which is it? Is it thermal or moisture? Right, it's moisture. Second thing is that all these assemblies that we're talking about, they form the enclosure. The enclosure, this is the summary, right, of the whole series here. The enclosure is absolutely that which does the heavy lifting. It's what you need to focus on. It's what you need to pay attention to. It's, I think these podcasts, these last 5, if they've done nothing else, it's to drill into your head that there's a lot to know, a lot to understand, and we have fully arrived at the point in our industry where specialization is basically required. Many of you out there listening to this, I actually would say realistically, it's not the case that you should try to know all this stuff. You should try to know somebody whose job it is to know all this stuff. That's an example of specialization required in an industry. The building industry is getting more complex. Oh my gosh, just think of the Internet of Things and building automation. I mean, it's blowing up. It's an exciting time. So the enclosure, think about the enclosure. You want a good enclosure. There's a lot of talk recently about passive survivability. A good enclosure is fantastic there. If your power goes out, how long before you freeze, or how long before you are overheating in that space? Well, the better the enclosure, the better it separates the indoor condition from the outdoor condition, the longer that is. But it's not just the enclosure. The intersection of the enclosure and the mechanicals, when the power is on, is that which actually drives the indoor environmental quality for you, right? It's not just about thermal comfort. It's about indoor air quality, sound, odor, light, vibration. All of it's important. It's all one thing, and we're living in it. And what we do to understand it, or working in it, is we break it down into these constituent pieces, and we think about them one at a time. So I hope you've enjoyed that, and I hope you enjoyed listening to my dog's collar jingle here at the end. And send us your questions, your comments, and let us know what you thought of this podcast and where we should take it next.
And we have a whole lot of really good ideas coming up in future episodes, so please stay tuned, and we really thank you for listening.
I had one idea I could have added.